The highest standard of industrial engineering prioritizes human operators over profit margins. It protects them from violent physical forces. While historic dangers were entirely visible, today's highest stakes live inside heavily insulated environments, specifically the continuous pharmaceutical cold chains of Hyderabad. The mechanical core of this system is the industrial screw compressor. Facilities expect these massive machines to run flawlessly for decades without a single interruption, but they operate under a rigid law of physics. Compressors are built strictly to compress vapor. Liquid, by definition, is incompressible. If a system loses superheat stability, liquid refrigerant enters the compression housing. This is known as liquid slugging. The mechanical valves attempt to compress this liquid, and the resulting hydraulic pressure instantly shatters the internal steel components. Industrial cooling failure rarely looks like a gradual mechanical decline. It is a sudden, violent hydraulic explosion that destroys the hardware and immediately halts production. To prevent this, the industry relies on an external safeguard, a temperature sensor, or thermistor, mounted directly to the outside of the compressor casing. These sensors operate under a severe physical constraint. They depend entirely on thermal conduction, meaning the cold anomaly has to physically transfer through heavy metal before registering a drop in temperature. The dense thermal mass of the steel casing acts as an insulator, creating a massive delay in the reading. We compare the two physical reactions. On the left, internal valves shatter in a fraction of a second. On the right, the external temperature reading stays flat. It takes 15 seconds for cold liquid to bleed through the casing and trigger the sensor. Thermodynamics move faster than mechanical conduction. By the time the digital alert actually triggers, the machine is already dead. Stopping liquid slugging requires a pivot in engineering logic. Operators must stop monitoring the trailing temperature of the casing and start tracking the mechanism actually controlling the fluid. That control point is the electronic expansion valve, or EEV. It dictates the exact volume of refrigerant entering the evaporator. Currently, facilities inspect these systems through periodic manual checks with a clipboard, or they simply wait for a low-pressure safety trip to automatically generate a maintenance ticket. Operating this reactively carries a steep penalty. An undetected leak leading to a sudden trip often results in an $85,000 emergency compressor replacement, plus the total cost of facility downtime. Upgrading the system with a continuous monitoring hardware array, installing pressure transducers, current transformers, and flow meters costs a fraction of a single mechanical failure. However, setting static threshold alarms on these new sensors fails in practice. Industrial chillers are highly dynamic systems that continuously adjust to shifting cooling loads. Hardware alone is insufficient. Without the correct algorithmic lens to interpret the data, adding more sensors simply creates unreadable noise. The actual target of predictive maintenance is mapping transient dynamic data. We have to look at how the system behaves while shifting between states, rather than measuring fixed, steady-state outputs. The earliest indication of a developing fault is a highly specific, microscopic drop. The system will show a subcooling decline of exactly 0.2 of a degree Fahrenheit per week. This drop is followed by a secondary confirmation signal, a steady, unnatural climb in the compressor's discharge superheat over that exact same time frame. These subtle thermal shifts culminate in a final warning. The expansion valve's stepper motor aggressively microfluctuates, losing stability under immense pressure. Looking at the valve and compressor actuation graph in panel A, we see sharp, erratic vertical spikes in valve position. Tracing the result down to panel C, the condenser pressure shows an aggressive upward curve following that exact instability. Identifying these specific transients provides a strict operational advantage. It grants a 4 to 12-week warning window before liquid ever reaches the compressor. The data required to predict mechanical failure already exists inside the system. It is hidden as mathematical transients rather than obvious alarms. Despite the math, facility managers remain deeply skeptical of highly sensitive AI. Models trained to aggressively detect microfluctuations inevitably generate false positives. In an automated environment, the immediate mechanical consequence of an algorithm flagging a false positive is a hard, unnecessary shutdown of the entire chiller unit. Inside a pharmaceutical cold chain, a sudden loss of temperature control means the ruin of an entire high-value production yield. This creates an impossible dilemma. The operator is being asked to trade a manageable mechanical risk for commercial ruin. You cannot deploy unproven, highly sensitive logic onto live equipment without risking the survival of the business. The solution is a safe, sandboxed validation protocol known as the 48-hour asymmetric bet. It requires zero live connection and carries zero operational risk. Step 1 is purely retroactive. You acquire 30 days of raw, historical SCADA logs from a chiller unit that has already suffered a documented compressor failure. Step 2 filters that raw data. Within that historical file, you specifically isolate the electronic expansion valve position logs and the suction pressure readings. Step 3 narrows the timeline. You isolate the exact 48-hour window immediately preceding the documented breakdown. Finally, you run a lightweight clustering AI algorithm exclusively on this isolated retroactive dataset. The success criteria is strict. The algorithm must successfully identify the exact mathematical erraticism of a stepper motor without any manual prompting. If the model accurately flags the event, the math is validated. This precise retroactive testing methodology is how a 91% prediction accuracy claim is proven in the real world. True engineering requires mathematical proof that tethers digital intelligence to the reality of physical hardware.